All right, so now I'm going to move on to part object B on worksheet 2. So I'm still in worksheet 2, and this page is probably going to be its own thing because there's actually a lot of information here. Now I'm looking at a position time graph. This looks like uniform acceleration. We'll kind of prove that it is in a second. But all right, so I'm looking at this object. Okay, what is the description I would use for this? Now some kids would say it's accelerating. That's true, but there's actually a lot of descriptions for acceleration. I'm going to be very precise with it. My object goes from a flat slope to an increasing slope. So that's, to me, tells me, okay, object B is speeding up in the negative direction. I want to clarify the direction as well, because you can be speeding up in the positive, right? But this is very clearly in the negative direction. All right, they want us to make a motion map. I don't want you to get too bogged down on this, but basically I just want to make sure we're all clear on what's happening here. So it's going to be qualitative, no numbers. First I'm going to do velocity vectors, and this is what you're used to. And basically what we would want to see is our velocity vectors are increasing over time. And the amount this velocity vector should increase by should actually be however big you make, the amount it increases by is these acceleration vectors. Now, so acceleration's in blue, velocity is in red. I don't want you to get too bogged down on this. To be honest, you won't see too much of this on tests and stuff, but this is a good visualization of basically this arrow gets bigger by this amount and this arrow gets bigger by this amount. Since it's constant acceleration, they should all be the same size, assuming that's true. We'll see if that's true or not in a second. All right, they want the displacement from 2.5 to 7 seconds. Now, some kids think everything needs a crazy calculation or something, but we want here is just use the position time graph, figure out the displacement. That's all we need. So 2.5 seconds to 7 seconds. Now it might be hard to see. This is halfway between. This would be 9 and 10, so I think that's like 9.5. And this one, all right, halfway would be 6.5 here. It's a little under, so I'm gonna round it to 6.3. It's up to you where you want to round it. So I'm going to say that's like about a third, and that's at 7 seconds. So the displacement is going to be, it ends at 6.3. It starts at 9.5. I plug that into my calculator. I'm going to get minus 3.2 seconds. Minus 3.2, not seconds, meters. And I was double checking on the calculator because I don't want to be wrong. So minus 3.2 meters. All right, then they ask us, what is the average velocity from that time span again? Well, I know velocity is just displacement over time, and I just found the displacement. So I can just do negative 3.2 meters over this time frame, which is 4.5 seconds. If I subtract 7 from 2.5, I'll get 4.5. And what I'll get is, look at that number. I should expect somewhere around like a third or 2/3. And I get negative 0.71 meters per second. All right, very precise number. We're just going to have these numbers for the rest of this worksheet, but that's fine. Negative 7.71 meters per second. All right, that's my average velocity. Let's try to find the instantaneous velocity at 2.5 and 7 seconds. Now, the way they want us to do this is using the slopes of tangents. So, just a reminder what a tangent slope is. If I have a circle is infinite amount of points, and really I can make an infinite amount of lines through this point. But there's only one line that actually goes through that point and nowhere else on the circle. So this would be the tangent point. This would not be tangent because it goes through the point and another point in the circle. So I'm looking for a line that goes through that point and only that point of the curve. So going back here, I'm doing this for 2.5 and 7 seconds. So 2.5, I'll do that one first. That looks like maybe just a little shallower. All right, I think that's the closest we'll get. And try to be as precise as you can, but as a grader, I'm not going to be super harsh on it. So what's fun with these tangent lines is that you can, as long as it's somewhat right, I will grade you appropriately. Like if I see you're trying to do the tangent line, it's a test. Some tests, like you're very strapped for time, I'm not going to try to hurt your grade or anything as long as I see you're doing the right method. What we need to do is find 2 points on this line that match it. So you can always grab this point where it started on, or you can grab 2 other points. And my suggestion is I like this point. This point's beautiful. It goes through 2 hex grids. So I know exactly what that number would be. Another good one, this one is pretty nice. As I said before, this is pretty nice. This one's all right. It looks like a 0.3 as well. You know what? I'm going to take these 2 points. So I'm going to take this point, which is 9 and 7. And I'll take this point, which is 4 and 9. About. It's a little bit under. So let's see what we get here. 9 and 7, 4 and 9. Let me not mix it up. So it's 7 minus 9 over 9 minus 4. I'll make sure I didn't confuse those 9s. Yeah, that looks right. All right. So I'll get negative 2 over 5, or negative 0.4 meters per second. All right, so that's my tangent slope for this time here. But I need 2 answers here. I need it for 7 seconds. So I'm going to do the same thing, and maybe you want to try and see how close we can get. So why don't you try on your own, make a tangent slope at 7, see what you get. Let's see how close we can get. We should be within 10%, I'm sure, if you do it right. So pause the video and see if you can do it. All right, I'm guessing you paused, unpaused, you did it. Let's see how close we get. So I have my tangent line here. I'm looking for 2 points that I like. This one didn't really end up as nice as the other one. I'll probably end up using this as a point. So my actual, my 7 and 6.3 will be a point. And let's see. This one's halfway. That looks kind of nice. Oh, I'll take this point. So this point is 5 and 8.5. Let's see what that gets me. So I'll do 6.3 minus 8.5, I think. Yep. And then that's over 7 minus 5. And that's going to get me 2's on the bottom there, negative 2.2's up top here. So negative 1.1 meters per second. All right. So this is my instantaneous velocity for t's at 7 seconds. So if you're confused by that, rewind the video, try to see. If you're still confused, you can always ask me. But I'm just trying to make a tangent slope, and I'm trying to find the slope of that value. And I should know from before position time graphs, that gives me a velocity value. So, when you take a tangent slope of that second, that should be the speed of the object right there. They want us to find the average acceleration, which is going to be the rate of change over time, or delta v over t. Now, what is my delta v for this? Well, I just solve for 2 velocities here. So if I go with v final minus v initial over t, that's going to be negative 1.1. Now, keep track of our negative signs, minus negative 0.4. So you can see here, this is going to become a positive number. This is a 4.5 second change. And what I'll get here is, so positive. This changes by a difference of negative 0.7 meters per second over 4.5 seconds. When I plug all this in, negative 0.7 divided by 4.5, I get negative 0.16 meters per second squared. And by the way, this number, I didn't mention it. If you get a little bit off, that's all right. It's based on your tangent slope. I usually give about 10% error range, or I'll just look at it and see what points are grabbing. And usually I can tell if there's an actual mistake, I'll be able to tell. If it's just slightly off, that's fine. So I get negative 0.16 meters per second squared. Every number has a purpose. So what is this purpose for this number? This is telling me for every second that goes by, my velocity changes by negative 0.16 meters per second. The negative being I'm increasing my negative velocity. Now they ask us, what is the instantaneous velocity at 4.75 seconds. And they have this explained here. So that might be a hint to you that maybe there's an easy way to solve this. And the easy way is I took the average velocity from 2.5 to 7 seconds. Right in the middle of 2.5 to 7 is 4.75 seconds. I'll prove that to you. 2.5 plus 2.25 seconds is equal to 4.75, or 7 minus 2.25 is equal to 4.75. So that's a sign. All right, that's in the middle. Here's another way. 7 plus 2.5 divided by 2, I take the average of them, you get 4.75 again. So, all right, I've proven 4.75 is in the direct middle. If you take the average velocity in a time range, you will get the instantaneous velocity of the middle second. So it should be negative 0.71 meters per second. Now there's another way I can do it. I have the two velocities here and here of that time range. So in theory, if I add up negative 0.4 plus negative 1.1 and then divide them by 2, this should give me a number that's fairly close to negative 0.71. And I get negative 0.75 meters per second. Now, you might say that's a different number. I agree. This is a different number than what I got over here. Let's just talk about why that could be different. To find the tangent slope, I had to actually calculate. I had to make a slope and then calculate points. I had to estimate where the points are. For how I got the negative 0.71, I did actually have to kind of figure out what the displacement is. I don't have any charts or anything, but it was a little more straightforward. I got the displacement from that time, I divided it by the amount of time it took place, and I got this number. If you're within this realm, if you're having to take tangent slopes, I force you to take the tangent slope to solve this. I'm expecting a range of answers because I know it's hard to be precise. So don't worry too much. As long as you understand the process, that's what's important. I would say this is very, very close to what it should be. If you're given the actual chart of information, I would say it's probably better to do the average velocity, but just know that if you take the tangent slopes, you are actually finding the exact speed at that point, assuming you do it correctly.